My name is Xavier. I work as a software engineer at Confluent. And today I want to share a little bit about some of the work I've done over the last couple of years working on Kafka Streams and optimizing, profiling some of Kafka Streams applications, and some of the things that we learned through that, and kind of give you some insights into what you can do for your applications. And even if you're not familiar with Kafka or Kafka Streams, this applies to any kind of JVM-based processes, so you'll be able to reuse that for other purposes as well. So the first thing I want to talk about is why would you want to profile your applications? Well, we're talking about streaming applications, so you want this to process data in real time. So it's very important to understand where your bottlenecks are and where you're going to start falling behind. Because once you start falling behind in your stream processing, you're going to have a hard time to catch up, and that's where you need to really understand where you need to optimize, and in order to do some capacity planning, understand what your limits are. Of course, you can use metrics for that, but oftentimes when people write applications using libraries like Kafka Streams, they don't necessarily collect the metrics from the underlying libraries. Kafka clients and Kafka Streams have a lot of metrics underlying. I don't see very many people actually collecting them. So most of the time, when you actually run into problems, you won't have those metrics available. And even if you did think about collecting those metrics, the reality is, if there is a metrics, that probably means that someone already encountered the problem before. And the problems that you're going to encounter will probably not be the same, and you probably won't have a metric for them. So until you actually encounter them, you won't know what to look for. And the last thing is that most of the time, you will not face those problems in testing at all. Most of the problems will only surface in production. And as Miguel said earlier, so doing this kind of canary testing is very important. And that's where you actually want to do your profiling, because that will give you the visibility into your application and really tell you exactly what is the bottleneck and what's happening. And some of the things that we'll learn today is that most of the time your application is spending is probably not in the code that you wrote, especially for applications like Kafka Streams-based applications, or anything that depends on a kind of a streaming library that applies to all of them. The code that you write will not spend that much time on a CPU. Most of the time will probably spend serializing the data, because every time you process any kind of message, you have to first read it from the network, deserialize it, then do your processing, reserializing it, and send it back downstream. And that can take a lot of time if you're not very careful about the kind of data structures you use and the kind of formats that you have chosen. And the last thing, of course, is that I/O matters a lot more, not only on the network side because you're doing streaming applications, but also because you have a lot of state management to do. So if you're doing any kind of aggregations on the fly with something like Kafka Streams or other streaming libraries, you will have the state that needs to be managed, and that can be significant. So my tool of choice for profiling is called async-profiler. It's kind of emerged in the last few years as one of the most simple and powerful tools to profile JVM-based applications. It can profile applications online. You can simply attach it to a JVM without having to set any arguments before starting it. You don't have to restart your JVM or anything. You just attach directly. And it supports older JDKs, 7 and above, so you don't have to be on the latest version. And you can profile container-based applications that may be running a different JVM that you're used to. And the nice thing about async-profile is that it merges both the JVM side of the profiling, so actually collecting stack traces from the JVM, but also collects the underlying system-level performance events and merges the two into like a comprehensive overview, which gives you visibility both into the JVM and the underlying native code and native libraries that you're using. And most importantly, it's very low overhead, so you can actually run this on an application in production without really impacting anything, or with very minimal impact, unlike some of the other profiling tools out there. There's some other good tools out there as well. I mean, some of you may know about Java Flight Recorder, which is now open source with the JDK 11. It has some powerful tools like mission control. And if you really want to go deep into the JVM side of things, you can use that. It's a great tool. It has more features than async-profiler, but it doesn't have the other side, which is the native code profiling. And one of the drawbacks of using it is that it doesn't. It does require, for most users at least, to upgrade to the latest version of the JDK. And I know a lot of people are not necessarily on 11 yet. And unless you have a commercial license from Oracle, you're not going to get that for early JVMs. So that's why I like to stick to async-profile. It's pretty simple. And in order to actually start running it, most of the time, this is all you need to do on your machine. So you can connect to your host. You can clone the repo, hit make, as long as you have some C++ compiler in there. You'll be able to just start profiling. This command line, in this case, will run the profile for 30 seconds, collect some samples, and spit out what is called flame graph. And I'll explain what that is in a second. You don't have to take pictures. I mean, I'll put the slides online, so you don't have to worry about that later on. So what is a flame graph? Well, a flame graph is this cool tool that was invented by this guy, Brendan Gregg, and he kind of popularized it. And it really gives you insight into where your application is spending most of your time. And it doesn't tell you only which functions are being spent the most time on the CPU, but it actually tells you what the call stack was at that time and where that call came from. So you can, and those graphs are actually interactive. I don't have the interactive information on the slide here, but you can actually drill down, and every single one of those bars here, the horizontal bars, you can actually click on them and then expand and look into more detail what's going on. So how does it work? Well, on the x-axis, it basically tells you, like, this is your CPU time. So from left to right, that's 100% of your CPU. That's where it spends. And then basically at the bottom, you have the main method that was called. And then as you go deeper into it, into the stack, you can see which parts of your application are actually being called. And this particular flame graph here is from one of the Kafka Streams application we run at Confluent. It does a fair amount of on-the-fly aggregations. And so I'll kind of walk you through what we can see here in this particular chart. First thing is this particular box on the left tells you that we're roughly spending maybe 15–20% of the time doing garbage collection. And that's something you will not see with a profiler such as JFR. And it may be able to tell you how much time you're spending in garbage collection, but this will actually tell you exactly which functions in the garbage collector are being called and what they're doing. So that can give you some insights. What this tells us is probably there's a lot of garbage being created in this application, and we probably need to do some work on making this a little bit more efficient and not create as many objects. The next thing is this is a Kafka Streams application. It's doing aggregations. So we're actually using RocksDB under the hood in Kafka Streams as a default implementation for state management. So there's 4 parts here. So inside of applications, you can see the calls. The green parts is the code that's running in the JVM. So that's the bytecode level code. So you can see all the class names and what functions, what methods are being called on those objects. The yellow and red code, those represent the native parts. So the native parts is where it calls into RocksDB. So the green to red is where the Java code calls into RocksDB, and it will tell us exactly what's happening there. We can see we're spending a lot of time doing some merging and of objects to do the aggregation. And on the left-hand side, this is the background compaction thread in RocksDB. So we're roughly spending about like 10 to 20% of our time doing compaction here. Which is expected because we're doing aggregation, but it's good to know how much time you're actually spending that, because that can help you tweak your RocksDB application. If you haven't started collecting any kind of RocksDB statistics, this can give you some hints as to what you need to do. And lastly, this is the Kafka pull loop. So this is the time we actually spend getting data from the network and deserializing it. Not spending too much time there. And the last little tidbits here, that's the actual code that we wrote. So we're not spending that much time doing actual computation. This is doing the actual, let's say, aggregation that we wrote. Everything else is just the library and all the JVM and all the other overhead. So if you're trying to look at the code and understand why it's slow, your code may not be necessarily where where it matters. And that's because streaming applications are very complex. So how you use the library, how you build the topology will affect the code quite a bit. And so you need to understand how this affects things. And typical metrics will not necessarily tell you all the picture here. So the way I like to think about how you're spending your time is to divvy up the thing into 3 portions. So the time you're fetching the data, including deserializing the data, the time it takes to process your data, including your own application code. In this case, also, I would include all the RocksDB and compaction and merging. And then sending the data, which includes serializing the code. And this way you can really it helps you understand where your bottlenecks are. Is it Are you spending a lot of time fetching the data? Maybe you do have some bottlenecks upstream. If you're spending a lot of time sending your data, maybe you have bottlenecks downstream. And if you're spending a lot of time processing data, then maybe you need to work on optimizing your code a little bit. Typically, it's very important also to have this data to do capacity planning, because CPU usage is a very poor way to estimate whether you're hitting capacity. Especially if you're using hyper-threading and things like that, you will typically max out at like 60 or 70% of your CPU for very homogeneous workloads. So you can't wait until you're hitting 90%, because that means you're already oversubscribed. And so what I like to use is basically to take the time you spend in all those three parts and compare it to the wall clock time that has elapsed. And if you are spending roughly like 80 or 90% of your time compared to what you're profiling, then I think it's time to start scaling up. So I'll go through a couple more examples of what you can do. So one of the things that we've used this for is detecting some of the unexpected side effects. So in this case, we basically had a Kafka Streams application where the cache was filling up very quickly. So there's a cache in Kafka Streams which basically, as you compute aggregates, it will not send an update downstream for every single aggregation, but it will cache a few before sending them down. And here we were seeing a lot of time spent in cache flushes. And this was like something completely non-obvious. I mean, there was some very inefficient code being called in the cache flushes in Kafka Streams, which are basically calling, as you can see here, maybe a seek operation in the RocksDB, and which could have easily been done as a get and put, which would have been much more efficient. But this code path was not obvious because it was deep inside the library. It would only be triggered when this cache was flushed. And so one thing that we were able to find out is that we were able to optimize it, and instead of spending 23% of our time doing cache flushes, seeking in RocksDB, we were able to get it down to 5% by replacing that with the simple get input. So that's the kind of insights you get from that you wouldn't get from just looking at metrics. So kind of like as a recap, so we had these cache flushes that we were calling inefficient methods, and those cache flushes were never really a problem in testing because the number of keys that we were updating in RocksDB were very few. And as we scale this out in production, we have a lot more keys. So basically, the cache was always full and always flushing with every single event. So we're able to improve this by an order of magnitude by doing two things. One is, of course, fixing the actual code and making this more efficient. And the other thing is, it helped us understand, OK, we need to increase the cache size here so that we don't flush all the time. Right? So if you have an application that has a lot of keys, if you don't want this to flush the cache all the time, you probably want to do this, want to have a bigger cache. That next thing is it helps you understand bottlenecks. So in this case, you can actually see all the way into the TCP stack and the kernel with the right kernel flags enabled. So this is the time we're actually spending writing to a socket during a Kafka Streams application, like sending the data. And this is the time we're actually spending just doing SSL random data. So when you write data in SSL using encryption, you have to generate a bunch of random data every single time. So you can see we're actually spending a lot of time doing random data generation, and the little orange part here is how much time we spent reading from dev urandom to get some good entropy for SSL. And so that's where it's important to understand where you're spending your time. You can see that using SSL is not necessarily cheap. It comes with a lot of overhead, so you should plan for it before you enable it. One thing that's useful is also streaming applications are usually do a lot of things at once. So your Kafka Streams library will basically do different combinations for different parts of the application. And so this will help you. You can actually split up the flame graph into a per-thread graphs. So it helps you understand if there are specific tasks in your application that are actually the bottleneck or really, because everything is one chart, it's hard to tell. So in this case, we kind of split it up. You can see across all four. And in this case, it's actually pretty well balanced. All four threads are doing relatively the same amount of work. But if you see any kind of weird imbalance here, then that means that one of your CPUs is going to be overloaded, probably. Next thing is lock contention. With Profile, you can just enable this e-lock feature. And now what it will tell you is that instead of looking at how much time you're spending on the CPU, it will tell you how much time you're actually spending off of the CPU and just waiting. And that's very important to understand where you're blocking, where you have some lock contention or where you're basically waiting on some I/O to happen. And this can help you understand where you're not very efficient at using your system. So this is an example of a startup of a Streams application. We're basically, during start, we're spending 130 milliseconds waiting on this consumer coordinator object. The nice thing about the flame graph, it'll show you at the top of the stack here what actual object is being locked on and waited on. So it's very detailed in really understanding where your bottlenecks are. And what this means in this case is you're probably spending a lot of time rebalancing the consumers because the consumer coordinator is responsible for that. And the other part is we're spending about 250 milliseconds in like creating metrics. So Kafka and Kafka Streams create a lot of metrics on startup, and they're all fighting for the same lock. And if you have like 8 threads starting up and they're all trying to create all these metrics, they'll all basically be waiting on the same lock to initialize all these metrics. So I mean, those some very simple example, but in practice, we've been able to use this to fix some timing bugs. We had some consumer.poll methods that would be called with a timeout, which is fine as long as data is coming in. You will never wait for the timeout to expire. But if it's in a critical loop and you have no data coming in on one of the topics, then you basically end up waiting for whatever timeout you have on that partition before seeing anything. So we were able to fix some non-obvious bugs in streams that were causing state restore to take a long time if there was no data flowing through some of the topics. And this way we're able to get our state restore from minutes to seconds. The last thing I want to talk about are like allocation profiling. This is where, with this simple extra feature, you can see how much, where you're allocating most of the memory, or where you're allocating the most objects. And that's extremely important to understand as well. This is an example of a stream's fetch loop. So when we're fetching the data from Kafka, what happens? And you see these like big, wide blue bars. And both of those are actually, what this tells us is we're allocating a lot of byte arrays and byte buffers. So there's a lot of copying of data going around. And maybe our serialization or our deserialization in this case is maybe not very efficient. And maybe we need to spend some time on like trying to minimize how many copying of byte arrays we're doing, how many steps we're going through. So with this particular allocation, it can tell us 2 things. One is we can see how many objects get allocated, so how many times we call a new byte array. But there's another mode where it can also tell you like how much overall memory you're using. And this is very important because if you understand where you're allocating all these objects, it can help you reduce your GC pressure quite a bit, especially if you're creating long-lived objects. And the next thing is you can also improve performance quite a bit. Because if you're creating a lot of large byte arrays, so let's say you're creating a 64 kilobyte decompression buffer with every single iteration, then that actually can take a long time to create because all that memory has to be initialized to 0. And so that if you are able to change your code and reuse the buffers, then that can help improve performance quite a bit. And so often you'll see those types of bottlenecks in the serialization, deserialization, and the code that does decompression and compression. So in this case, we were actually able to improve the Kafka Streams client for small messages by about 30x in terms of performance compared to what it was before by just being able to reuse some of the buffers. And those are the bugs that have been around for years in Kafka that no one really noticed just by doing this profiling. We only have 1 minute left. I want to touch a little bit on containers because profiling in containers is a little bit more tricky than on bare metal. We probably won't have time to run through everything. But the basic idea is that you need to be able to put the agent somehow into the container you're profiling. And there are many ways to go about this. You can actually put it into the image as you build it. Or if you're using third-party images, you have to do it ad hoc after the fact. From the host, you probably still need host-level access to tweak some of the kernel settings before you can do the profiling. So the most contrived case I've encountered with that is Google Kubernetes Engine. Because it has a lot of restrictions on what you can do. You can actually not do anything on the host machine. So this is as complicated as it'll get. You can't install anything directly. And they take containers to the extreme. So if you want to run anything on the host machine in Kubernetes, in GKE, you actually have to run it in a container as well. So everything has to run in a container, both your application and your profiling tools. So they have this toolbox container, which is very nice. You can actually just call it toolbox, and it'll give you an environment in a container with a shell. You can install everything you need. That's where you'll probably do install your profiler. But then you have to actually go back outside of the toolbox, copy it into the container, and then make sure they're all the same path and everything. So before setting the kernel options, and then you can go back into the container and then finally execute a flame graph And the funny thing is that the flame graph will actually be, the path is resolved inside of the target container, so the file gets created not in your toolbox, but in the other container you're profiling. So then you have to go back outside the toolbox and carry it back out. As an exercise for you, you can do this and at home and maybe optimize this a little bit more. But this is basically how you go about it in a container environment. A little bit more complicated, but I want you to try this at home. Here's a couple more resources. Async-profiler, Confluent. Thank you.